Hello class, welcome to today's video. The first thing I'd like to do is spend a few minutes going over the work you did last Thursday, or some of you may have done it as makeup work later on during the weekend. So it was the factoring and then the verifying algebraically problems. And I asked that you spend 20 minutes on it. You're welcome to spend more. And you also needed to try every problem, but I totally understand that you may not have gotten all of them correct. All right, that's how this chapter works sometimes. So let's go through some of the answers. This way I can get some feedback, see how it went for you. And also with this, I can count this as checking your work Thursday. So here's number one. To factor, you get two sets of parentheses, and you can have these factors in the other order. So if you have cosine x minus 1 first and then cosine x minus 4 second, that's fine. And then this is the structure of this, and I often like to write that. So question for you, do you just jump right in and factor, or did you write it with x's first? Okay, next question. Can you please type in your answer for number 2? What did you get when you factored that expression? All right, you should get this. And again, it's okay if your factors are in the other order because multiplication is commutative. But the 2 has to be with the 5 sine x and the 3 has to be with the 1 sine x in order to make your outers 15x and your inners 2 sine x come out to 17 sine x. Number 3, did you have any ideas? Did you get it? Anyone figure out how to factor with those 4 terms? It's grouping. So if you look at this, you have 4 terms, and if you didn't notice that before, that's okay. But when you have 4 terms, grouping is often the way to go. So if you look at your first 2 terms, they have in common this term. These 3 factors make 1 term. These 2 factors make 1 term. What they have in common is 3 sine x, because there's a factor of 3 in the 6 here. So we can take out a 3 sine x. When we divide this by 3 sine x, we're left with secant x. When we divide this by 3 sine x, we're left with negative 2. And over here, for these 2 terms, they have a factor of 5 in common. And this is your work step. When you do grouping, you get a work step. And then what you need to do is take your, I call them the mini GCFs, because this is the GCF of these 2 terms, and this was the GCF of these 2 terms. You take those, make one factor, and use your repeated expression once. And you can always check your own factoring by multiplying it out. If you multiply these 2 together, you get 3 secant x sine x. Even though you might have secant and sine in the other order, multiplication again is commutative. The outers will give you minus 6 sine x. The inners will give you plus 5 secant x. And last times last will give you that minus 10 we wanted. Okay, let's make our way down to verify algebraically. What I have for you here are 4 different ways to do this. So let's see what we can see at one time. Let me zoom out a little bit, and you'll be able to see a little bit more. Okay. So I think with that, we can see all 4 of my options here. And these are not the only 4 ways to do this. So I'm going to kind of zip through this. If you want to spend longer looking at it, just pause the video. And if you did it a different way, and you want to know if you're correct or you want me to see it, I'd love to hear about it. So I think the most common way that you guys are going to do this is this one or this one. If you split apart, because there's a 1-term denominator, you can split that apart. This becomes a Pythagorean identity, and then you end up with sine squared. If you wanted to show the side work for that, it would look like this. So if anyone wants to show the side work for changing 1 minus cosine squared into sine squared, you can start with your basic Pythagorean identity. And then we know that 1 minus, if we move the cosine squared over, cosine squared equals sine squared, we could make that replacement. You don't have to show this side work, but it's totally okay if you want to. The other thing I think most people may have tried was this. Did you notice that secant squared minus 1 is a Pythagorean identity? Because this is a Pythagorean identity right here. And if we rearrange this by moving the 1 over, we see that secant squared theta minus 1 is equal to tangent squared theta. You then can change everybody to sines and cosines. And there's a whole bunch of different ways to get from here to here. But this is just one way. I use same change flip. So I'm guessing most people did one of these 2. Those of you who like to take one term and turn it into 2, when you had the secant squared up here, you can change that into tan squared plus 1 because it's a Pythagorean identity. Your 1's cancel, and you get to the same place that I was here. And check this out. See that these match? So one way to simplify this is change everybody's sines and cosines. Another way to simplify that same expression is to split this up into tangent squared times 1 over secant squared, because then you can change that 1 over secant squared into cosine squared and not have any reciprocals anymore. Kind of nice. Still get to sine squared. And then I thought of this one last minute, so I thought I'd throw this in as well. You may have changed everybody into 1 over all the secant squareds into 1 over cosine squared. And then to clean up this complex fraction, there's tons of ways to do that. But one way is to distribute cosine squared up top and multiply cosine squared on the bottom. And you're allowed to do that because this has a value of 1. You can multiply by 1 whenever you want. And I'm curious which of these, if any, did you do? Did you do, I'll call them A, B, C, D, or did you do something different? Okay, up next is number 5. I'd like to know what strategy you tried for number 5. So here's the list of strategies. And for number 5, I think you worked with a more complicated side first. I'm sure you substituted using identities, and I'm sure you were brave. So I'm not looking for those answers right now. So for number 5, did you FOIL? Did you factor? Did you add, subtract fractions? Did you split apart a fraction with a monomial denominator? Did you start with a Pythagorean identity? We didn't learn this one yet. Or did you start by changing everything to sines and cosines? So did you try 3, 4, 5, 6, 7, or 10 first? Okay, I'm going to guess most people went about this by getting a common denominator and subtracting those fractions. So your common denominator is secant tangent. When you get this together, you get a Pythagorean identity. And then a lot of people, I'm going to guess, got stuck here. They knew that this came out to negative cosine cotangent, but they weren't sure how to show that step. So you can pull this apart. You can make that negative 1 over tangent times 1 over secant. And anytime you're not sure if you were allowed to pull apart that fraction, if what you did was acceptable, try putting it back together. So if you do top times top, you get negative 1. Bottom times bottom is tangent secant. And this is equivalent. If you wanted to go one step more and actually swap the order there so that you have cosine first and then cotangent, that's cool. Please take a look at your work. Make sure you have x every single time you have a trig function. Or in the previous one, make sure you have theta every single time. You don't want to have a secant squared with like nothing in it. A secant squared with nothing in it is, I mean, picture this. Picture if I ask you to solve that equation. It makes no sense. So when you have a trig function that doesn't have a variable in it, whether it's theta, alpha, beta, or a number, it could be a numeric angle, it just doesn't make sense. It's like having an empty square root, okay? Now for number 5, for anyone who tried to change everything to sines and cosines, it works, but I don't think you'll like it. I think you'll agree. I think it's more work. So if you change everybody to sines and cosines, I same change flip this and same change flip this. That's not the only way to simplify that, but that's what I went with. And then after I reduced, I had to get a common denominator anyway, then use a Pythagorean identity. And then I had to split this up in order to get down to negative cosine cotangent. If you'd like to look at this longer, just pause the video and feel free to use the Google Doc. Let me know if you have any questions on any steps or if you have a different way you want to do it. You can always take a picture of your work and insert that picture in the Google Doc. You don't have to type everything you did. And let's move on to number 6. So for number 6, here we go. Here's 2 ways to do it. I can't show both at once. So let me show what I think most people did. I'm assuming most people split up because there's a one-term denominator. And then pretty quickly, this actually comes together. Whenever you see a squared, you want to think Pythagorean identities. So 1 minus sine squared can replace with cosine squared, and we're actually finished. Just to give another option, because I was trying to think of other ways to do this. Here's an option I thought of. I rearranged the minus cosine and the minus sine cubed. Because if you look at this grouping, they both have sine. So you could factor GCF just out of those two. So I factored out a sine I just copied the minus and copied the cosine. They have nothing to do with what's going on right now. But I see that these both have a sign, so I factored it out, got a Pythagorean identity, replaced that with cosine squared. Then I split it apart, and it actually works out fairly quickly. I think the other way was easier, but I think this worked. And just curious for number 6, did you go about it this way? Did you start out by splitting this into 3 fractions, or did you do something different? Okay, thanks for watching this part. So with your responses there, that we got to go over the answer key, and I also can go ahead and give you credit for the work from Thursday. All right, let's get into today's lesson. So what we're going to do is we're going to do one more verify algebraically, showing all the steps, and that's going to be using a strategy we haven't used before. So we're going to create a Pythagorean identity. And here's the problem we're going to try. So taking a look at this problem, we could start on either side because both sides actually look fairly complicated. But what I'm going to do is I'll show you a little bit of work on the left-hand side, because I think a lot of people might think to make this 1 over cosine and sine over cosine, and then you can add those together, and there's nothing wrong with that. So it's a good idea because it gives you some options, because now when you work the right-hand side, if you can get it to say secant plus tangent, you're all set. If you can get it to say 1 plus sine over cosine, you're all set. You don't have to match the original. You can match any step along the way. But if you try to work the left-hand side, I think what you're going to see is that you kind of get stuck here. So it's the right-hand side that I want to focus on. And if you look at this, there's really no good way to pull it apart. So if anyone's looking at this and thinking, can I make it cotangent over cosecant minus cotangent over 1, you cannot. That is illegal algebra. You can't do that because, see, the denominator has 2 terms. You can't pull apart in that fashion. When you have a 1-term denominator, you can pull this apart, you keep that denominator, and then you put each term of the numerator up top. When you have a something like this, we had this in one of the problems earlier, this format, we had 2 factors in the bottom, but that's still 1 term. You can pull this apart. You can make this like x over y times 1 over z. If you're not sure if that's allowed, try putting it back together. Top times top, bottom times bottom gives you this. Or you could do x, or you could do 1 over y times x over z. That would also be a correct way to split this apart, because if you do top times top and bottom times bottom, you get this expression. But the structure we have here is more like this. See, it says we have a 2-term denominator. And so if you're thinking, can I do this? The answer is no. And we can justify that you can't do that pretty quickly, because if you try, hang on. Okay, I think that's what you'll try to do. You can't do that. You also can't do what I just had. But this is the one I think you'll try. And if you try to put it back together, you need a common denominator of y times z. And what you would get here is xz over zy minus xy over zy. And you can see when you put that together, that is not the same as this. So there are lots of fractions where you can pull apart the fraction, but if your denominator has 2 terms, it's not very likely. So just be careful with that. And let's take a look. So we can't pull this apart. We could change everybody's sines and cosines, which actually would work, but I'm not going to go that route because I want to show you this new method. So the new method is to create a Pythagorean identity. Here's when you try this. Do you see in the bottom that it has 2 terms? And if this one were squared, it would be a Pythagorean identity, because 1 plus cotangent squared equals cosecant squared. So if this cosecant were squared I would have a Pythagorean identity and be able to replace that with cotangent squared. So that is the situation we have here. So the question is, how do I get the squared in there? What most people think is they want to go in and square this expression, and you can't. That's illegal algebra. You cannot just square an expression. You can pull apart fractions sometimes. You can multiply by 1 whenever you want, no matter what that 1 looks like. But you can't just go in and square an expression. So then some people say, well, what if I do it to both sides? Okay, well, then you're breaking the rules because you're only allowed to work one side at a time. Furthermore, even if you squared this, what you want to happen is not going to happen. Because if you square cosecant x minus 1, it doesn't just square the cosecant, and it doesn't just square the minus 1. Because when you square something, it means to multiply by itself. So what you'll get is this, and you'll have this extra term in the middle that you don't want. All right, so even if you were feeling pretty adamant that you really want to square this, you can't, and it doesn't do what you want anyway. So how do we go about this? I want to get a squared here, but I want to keep the minus 1. Well, here's what you do. You multiply the top and the bottom by what's basically the conjugate of the denominator. So do you remember when we did complex numbers? Let me start with complex numbers. When we did complex numbers, way back in chapter 2, the conjugate of this would be 3 minus 5i. You keep the real part the same, you change the sign of the imaginary part. When you learned radicals last year, if you had something like negative 2 plus radical 6i, the conjugate would be negative 2 minus radical 6i. You keep this part the same, you change the sign of the imaginary part. So what we have here is, in the denominator, I have cosecant minus 1. If I multiply top and bottom by cosecant plus 1, and you have to do top and bottom by the same, because look at this fraction. What's cosecant plus 1 over cosecant plus 1? It's 1. So I can multiply by 1. It's going to change the way this looks, but it's not going to change the value. So up top, you have the option to distribute. I'm going to keep that factored when using this strategy because I know what's going to happen later. So when you're doing create a Pythagorean, it is likely you want to keep the top factored, but go ahead and FOIL the denominator. You cannot reduce this right now. You can't reduce cosecant over cosecant squared because cosecant here is part of a factor. The top has 2 factors. It has cotangent and then this 2-term factor. But what we can do, some people might be thinking, can you factor this and then reduce? Yes, but that'll take you back to here and then you reduce that out. You're back to where you started. So although you can factor this one, you don't want to. Think about why we did this. We created a Pythagorean identity so that we could replace cosecant squared with cotangent squared. And now, because my top has a factor of cotangent and my bottom has cotangent times cotangent, because that's what cotangent squared is, I can reduce this and one of these. And we're not quite done yet, because if you look over here, I don't have that, I don't have this. But if we go ahead and change, there's 2 ways to go about this. We can change everybody's sign over cosine, or sines and cosines, I'm sorry, or we can pull it apart. Let's do the pull apart. The other way works just fine as well. Okay, so taking a look, this is a little messy, but 1 over cotangent is tangent. So if this comes out to secant, we're all set. So let's change this to 1 over sine over cosine over sine. Don't forget the x every time you write a trig function in this one. In some problems, it'll be alpha or beta, but in this problem, it's x. And when you have 1 over sine over sine, it's going to become 1 over cosine. You can simplify this lots of different ways. You can do same change flip. You can multiply top and bottom by sine if you want. That's actually my favorite way. But I did same change flip because I think that's your favorite way. So I have 1 over cosine plus tangent, which comes out to secant plus tangent. which matches what we had up top in the original, and we're all set. If we had matched this step instead, we could stop there, no problem, but I happened to match the original secant plus tangent, so this work that I did here was actually unnecessary this time, but not wrong, nothing wrong with it. So this is when you should possibly try to create a Pythagorean identity, and this is how. So if you didn't get a chance to write that down before, pause the video so you can write it down, and we'll continue on our way in just a moment. Okay, so let's continue on. And what we're going to do next is I'm going to ask you to locate your graphing calculator. So if you don't have one, access that one from the NJSLA Park website, please. And we're going to look at verifying graphically and numerically instead. So when I give you an identity, so like this side is equal to that side, if I ask you to verify algebraically, this side will be equal to this side every single time. Okay, I'm not going to give you something that doesn't work. However, in real life situations, or if you're doing something that's multiple choice, or if you're in AP Calc, you might not know if this side is equal to this side. So instead of trying to do all the work algebraically to find out, because that can be very difficult and time consuming, and one little mistake might not let it work out anyway, another option is to graph on your calculator. So if we graph the left-hand side on our calculator and the right-hand side on our calculator, if they're actually equal, they should make the same graph and they should have the same table. So that's what we're going to do. So again, if I ask you to verify algebraically, the two sides will be equal. I won't try to fool you on that because that makes your life a lot harder, and I don't want to do that. But let's see if these two sides actually match using a calculator. So we're going to graph the left-hand side. It's common to abbreviate that LHS. That's not me being lazy. That's a common abbreviation. And when you go to put this left-hand side in your calculator, because this has two terms, you need parentheses around that denominator. When you hit sign, the calculator is going to open parentheses. You have to close them after you put the X. You have to close them around the denominator as well. So you need parentheses around that. And then the calculator, because when you hit sign, it's going to open them here. You actually have to double close them. And then you'll have plus 1 over, open your parentheses because you have two terms in the denominator. And then when you hit sign here, the calculator is going to open them. If you have the TI-89, you have to close them twice in order for the calculator to graph. But if you have any of the 84s or 83s, you can actually leave them hanging. You don't have to close them at the end, but you can if you like. And then for the right-hand side, when you go to put this in Y2, you're going to have 2 times secant squared. Now, we don't have a secant squared button, and we actually don't even have a secant button on our calculator. So to graph 2 times secant squared, what we need to realize is we have 2 times secant squared, and since we don't have a secant button, we're going to have to use cosine. So we want to graph 2 times 1 over cosine squared. And to do that, we can't put the squared here. That's not how the calculator allows us to do this. So what we have to do instead is we have to remember what cosine squared is. Cosine squared is where you take the cosine of x and then you square it. So cosine squared x is taking the cosine of x and squaring it. In the calculator, it's cosine x, close parentheses, and then squared. The calculator will read this as find the cosine and then square it. And I know that looks kind of confusing because some people think that you're squaring the x. You're not. If you were squaring the x, this is what it would look like. The squared would be inside. So to get cosine squared, you can do cosine of x and then square. And that's going to give you 2 times secant squared. Okay. So another option, by the way, if you're uncomfortable, if anyone's looking at this and thinking, but it really looks to me like you're just squaring x, we're not. The calculator is going to find the cosine of x and then square that quantity. But if you're uncomfortable with that, another option for you is to double parentheses this. I wouldn't do it because more parentheses, if you put extra parentheses, if you put them in the wrong spots, it can go wrong. So if I were you, I would just kind of get yourself comfortable with this to show cosine squared. But this totally works too. Okay, so get those two in your calculator. Okay, and getting these into the calculator correctly can be half the battle. So that's something you actually kind of want to practice as we go here. So this is my first one. It's my left-hand side, right-hand side. And on this calculator, my left-hand side, I have to scroll to the right to see the rest of it. And the right-hand side is, I think, pretty clear. And when you graph, if you have the newer color and graphing calculator, make sure you're in radian mode, zoom trig. Go to radian mode first, then zoom trig. When you graph on the newer graphing calculator, you're going to know if these are equal to each other because you have the color graphs. So here's my left-hand side in blue, and then my right-hand side is going to come in and graph, and it's red. So you can see that it's overlapping perfectly. Now, if you have one of these calculators, which does not have the color grapher, it's hard to tell if you have the same graph because maybe it's not the same graph. Maybe the other function is somewhere outside of my viewing window. So one thing I want to show you is that you can go to your y equals. And if you go to the left of y equals, and you guys with the color calculators can do this as well. If you click on this thing to the left here, you can hit enter on the older graphing calculator. That will graph a thicker line for you if you want. See that? You can hit enter. That actually does shading. That's for inequalities. That's your greater than inequality. Okay, but that's not what we want right now. This would be shading below your less than inequality. This one right here is pretty handy. It looks like a -0. And if you, actually, I want to do that on Y2, not on Y1. Sorry about that. So Y2 is really where I want to do that. And on the newer graphing calculators, you have your darkened graph, your thicker graph, your greater than inequality, your less than inequality. You have that feature as well. And it's actually, again, on the second graph where I wanted to do that. Okay, because what'll happen, this is what I want you to watch. What'll happen is when the calculator graphs, it's going to show you where it's graphing. And that doesn't seem very exciting as you're graphing the first graph. However, as we graph the right-hand side, you can now see that you're tracing right over that function. So you can verify that sure enough, they appear to be the same graph. So I believe the left-hand side is equal to the right-hand side. You can also go ahead and look at the table if you want, no matter what your settings are. So my settings are a little funny right now, so you might not have the same numbers as me. But do you see for each x, the y's match? For this x, the y's match. For this x, the y's match. And that should happen. If you see error, that means that something's undefined. And that's our first one. Let's go ahead and get more practice. And the real skill here is putting these into the calculator, because I think the concept is fairly clear. If these two are equal to each other, if the left-hand side is equal to the right-hand side, then their graph should match. But getting this into the calculator, I believe, is the challenging part. So for the left-hand side, we're going to do y1 here. And there's no cotangent button. So I'm going to do 1 over tangent, and we're not going to use theta. We're going to use x. If you were wondering, can you do cosine over sine? Sure. I tend to use 1 over tangent for cotangent instead. The denominator is 2 terms, so you're going to need parentheses around 1 over sine, because we don't have a cosecant button, minus 1. And when you do this, you don't have to write down what you're going to put in the calculator, but a lot of students find that this really helps them get their graphs right because they're planning ahead. So they know when they go to type this in, that when they go to type this in, they're going to do 1 over tangent, and this helps them remember that the calculator is going to open the parentheses. They have to close them before they do divided by 1 over sine, and then the minus 1. So that's why I'm writing it out the way I'm writing it out. Now, for the right-hand side, you got to be careful because this may come as a surprise. The numerator requires parentheses. I think we understand that because it has 2 terms. The denominator is 1 over tangent is what I'm going to use. Also requires parentheses. And that might be the surprise for you right there. So even though this is 1 term, because I have to write it as 1 over tangent, I need this in parentheses because what the calculator is reading this as, this is cosecant plus 1. And we're going to divide that entire quantity by this entire quantity, which is cotangent. If you don't have the parentheses around this denominator, what the calculator will read this as, so if you don't have parentheses around 1 over tangent, the calculator is going to read it as, take this and divide it by 1. Well, that means nothing happens. And then divide it by tangent. So now instead of your denominator being cotangent, your denominator is only tangent. So that's why the parentheses, even though this is 1 term, because we're writing it as a quotient, we have to put parentheses around it. I told you this could get tricky. All right. So, but don't stress over it. This is really just something we're practicing. Okay. So there's no need to get stressed about it. We practice it this year, and by the time you get to the AP Calc exam next year, you'll have everything down. Okay, and I'd be saying the same thing even if we were in school together. All right, here we are. I'm going to set this to be the tracer. So it's hitting enter until it says -0. And here's the graph of the left-hand side. That's kind of a neat graph. And then we're graphing the right-hand side now. That's a little error there. I had the extra circle there for a little bit. I don't know. But the 2 graphs do appear to match. And if we take a look at the table, let me reset my table. To the usual. Oh, there's that error. See, that just means at 0, it's undefined. But for each x, the y values match. So it looks to me like these 2 are equivalent to each other. All right, and we're going to have a peek at one more example. So here's our next one. We have tangent cubed plus 1. I want to know if that equals secant cubed. So to graph the left-hand side, we'll do tan x to the 3rd. And again, if you're more comfortable having an extra set of parentheses around the tangent, feel free. But extra parentheses sometimes can actually make your life harder. The calculator will do tangent and then raise that to the 3rd. Oops, I forgot the plus 1. And this one here is secant to the 3rd. So I'm going to use 1 over cosine, and I'm going to raise that to the 3rd. So we want to see if these 2 are equivalent. So in the calculator, I have tan x to the 3rd plus 1, and I have 1 over cosine x to the 3rd. And let me put that tracer feature on, and we'll take a peek. So that's what the left-hand side looks like. And here comes the right-hand side. That is not the same. These 2 are not equal to each other. So it's a quick way to tell. If you get good at putting these into the calculator, a quick way to tell if the expressions are equivalent is to graph them and see if their graphs match. So these are not equivalent to each other. And what I have last for you today is a little bit of practice. I have 2 problems for you to try. So what you're going to do is please write this down. You can try it later. This is the problem from a little bit before. 1 over 1 minus sine x plus 1 over 1 plus sine x. And we know that's equal to 2 times secant squared. I'd like you to verify that algebraically, please, and show all your steps. I'm not going to give you the answer now. At the beginning of our next lesson, I'll show you some solutions because there's a bunch of different ways to do this. And please don't spend a ton of time on it. Give it a try. If it doesn't go well, maybe revisit it another time. But there's no expectation that you're spending hours and hours on this. That's not what I want you to do. Okay? And then the last thing for today is for you to try this calculator problem. So this one you might have to do now while you have the video handy, so you don't have to pick up the video again later. But this is a multiple choice problem to see how you're doing with getting these expressions into the calculator. So which one of these is the graph of that? Again, I'm not going to give you the answer now. I'll reveal the answer at the beginning of your next lesson. Thanks for watching, guys. Have a good day.